So I hope so. Let's start. Uh, uh, what I'm going to speak about. I was walking with my son. His name is David. He's 5 years old, and he said me, "Dad, what is the biggest number?" And says, "I know 10,000,043." And then he said, and in the children garden, someone says that this is infinity, and infinity is the biggest number, right? So I said him right, but he was not right. And I decided to do some presentation about the numbers and what is the biggest number we know. It is obviously because we are speaking about natural numbers, so there are infinite number of numbers, and when you point on some number, you have a rule that this number plus one is the next number. So I will not say all the numbers, all the infinite numbers. I suggest a journey on the axis of natural numbers from smallest one to infinity. And we will stop in interesting pit stops. So fasten seat belts. Each time I switch gear, I go to the bigger and bigger class of numbers. So there are risk of headaches, vertigo, and addiction to math. Let's start. We are starting from real life. From the first number, that most important number, it is generator of all the numbers, is one. One is you, me, and from this building block, all the numbers are constructed. Number of planets of solar system, 9. And I know about Pluto, but since Pluto was excluded, another planet was found. So it is 9. Numbers of letters in English alphabet is 26. Days per regular year, 365. Diameter in Earth, 12,756 kilometers. Oxford Dictionary is near to 200,000. Number of people in Gush Dan, Tel Aviv agglomeration, and is almost 4.5 million. Total number of Wikipedia articles, I think it is English Wikipedia articles, is almost 6 million. And total numbers of humans on Earth, 8 billion. And you see, even on first slide, we started to use some weird words as illion, million, billion, because the numbers itself is not enough to describe the big amount. So we're going to our first notation. It calls scientific notation. And his formula is here. It is 1,000 multiplied by 1,000 in some power, and this power gives the name of the number. So billion is 2, trillion 3, quadrillion 4, and so on. So we have all this scale up to centillion. And you maybe know, maybe not, but there is no object in our universe which we can count with centillion. So maybe we reach the end of the scale and we can stop. There are someone, I talk with my friend, and he says, stop, but you know that you have gazillion, which is much bigger than other numbers. And it was a joke about George Bush Jr. About he heard a news, and in the news someone says 2 Brazilian soldiers were killed yesterday. And he said, 2 Brazilian, how much is it? we will not stop on Brazilian, we will go to other numbers. But why we use scientific notation? For example, we use it for astronomic numbers. So total number of stars in Milky Way galaxy, our galaxy, is 100 to 400 billions. Number of Rubik's Cube combination, 43 quintillion. Total number of grains of sand on the Earth is these numbers. It is almost 6 trillion. Total number of stars in the universe, 200 sextillions. Number of atoms in the Earth is 10 in power 15 or 50. Total number of 52 Descartes is 10 in power of 67. And number of fundamental particles in the universe, observable universe, is 10 in power of 80. And we reached the first interesting number of Googleology. And actually, this is the number we start this discipline, or I don't know if we can say science, but this discipline of mathematics is Googleology. It was invented in 1920. The Edward Kastner, this mathematician, working as I started this lecture with his nephew, Milton Sirota, and they spoke about the big numbers. And his nephew say, I want to invent a huge number, the biggest one, which have name, and he called it Google because his favorite character of the comics was Barney Google, this guy. So he called Google on name of Barney Google, and this is the Google. It is 10 in power of 100. Another interesting number we know is the Shannon number, the number of all possible chess games combinations. It's 10 in power of 120. Now we know that he counted illegal moves. So the real number of possible legal chess games from the start and by sequence of move is much, much smaller. But this number is much more than number of atoms in our galaxy, much more than number of particles in our universe. That's why we say that we cannot count chess till the end. For example, the checkers game has around 4 billion combination, and it was solved. All combinations were computed and stored in some database. And the last astronomic number, the Planck volumes in the universe. So Planck volume is the smallest volume where physics makes sense. We don't know what is going on if it is something below this scale. So it is minimal unit of measure in our universe, and the volume of universe is 10 in 185 Planck volumes, and it is much, much, much smaller than centillion. So I'm gonna ask, so centillion is the biggest number? No, we just starting our journey. So we go into gear number 1 or gear number 2. Beyond normal numbers, this is the numbers which we cannot, or it is very hard to write in a regular way. We must to use scientific notation. So we have Google Chime is 10 in the power of 1000, or millillion is 10 in power 3003, or Google Gong is 10 in power 100,000, or just below of 7 factorial. And here we can these numbers are much bigger than any we have in our universe, but still we have many interesting problems in history related to these numbers. And the first problem is Archimedes' kettle problem. We have poem from 3rd century BA from Archimedes, which described his problem. We will not read this problem, but he has 4 herds of cows, different colors, different sexes, and he describes a couple of equations, what part of black related to white, related to yellow, and so on. And he finished his poem by saying, who can solve this problem? It is a really smart man. So I will not give you to be a smart man. I sure that in 5 seconds you can solve it. But this problem was solved only in 1965 with the help of computers, supercomputers, and the minimal number of such hertz is 10 in power 206 Aleph. Another interesting number is from Jorge Luis Borges, one of the most impactful persons in 20th century. He was a writer, poet, translator, and one of his books, Library of Babel, describes library of all possible books. So you have books with infinite library with shelves. On the shelves you have book with 410 pages, 40 lines, characters, and so on. So if you count all the possible books in Library of Babel, you have a number 10 in almost 2 million. And the prime numbers. We know what is the prime numbers. It is hard to find prime numbers. And in 17th century, mathematician Marin Messiaen found some rule that says that some numbers of kind of 2 in power of n minus 1 may be primes. And moreover, 2 in power of prime number minus 1 may be prime. And it calls Messiaen primes. It is both of them called Messiaen prime. So there are schools that says only this is a Messiaen primes, and there are mathematicians that says all these numbers are Messiaen primes, but it is related to another competition in mathematical world, who find the biggest Messiaen prime, and the largest for now found in 2018, and it is 2 in power 82 million 5. I will not call it, so you see it. And unless it is unreally huge number, it is the number. So we can say the last numbers of this prime. This is the last number of this prime. You can check all this number that it is a prime. So I want to return to these strange errors. You see already 2 in the 82 million. It is hard to write in the normal notation, and we need more powerful notation to describe the larger numbers. So we go to new notation. It is called Knut error notation. And briefly, it is very easy. Let's say that we have a ring, the numbers, and we have some operation on the ring, which says operation 1 of the ring is number and b copies of the number which is neutral to multiplication. So it is a plus b copies of 1. The second level is a and b copies of hyperoperation 1, previous operation. So here you have a plus a plus a plus a plus a. Next level is a and b copies of previous operation. So it is a multiply b or multiply a or power. And this is called Knut's error. And then you can extend this notation and set level 4 is titration for hyperoperation. It is a arrow, b copies. Or it is the tower of powers of a of size b. So for example, 4 titration 3 is 4 in power 4 in power 4, or it is something like 10 in power 154, and this is the common case. So for now, we go into third class, which is a class of which is we almost cannot write in normal notation. We must to write it in the scientific notation or Knut notation. And here we have Googleplex is 10 in the power of Google, or 10 in power 10 in power 100. Or Excentoplex, it is 10 in power 10 and power of 303. Or we have Googleplexigon, which is 10 in power of 10 on power 10 or power of 5, or 10 in power of 10 in power of 100,000. Or Google Bank, which is a factorial of Google. It is something like 10 in power of 10 in power 101. Till now, we're warming up, and now we're going to slightly large numbers or slightly annoying numbers, because this number you cannot, it is hard to write with the even scientific notation. For example, exillion is 10 in power 10 in power 3 quintillion. And the last, let's say, real number that we see here, there are one of the outcomes of string theory says that maybe we are in the multiverse. We have not only our universe, we have many of universe, and size of all the multiverses less than 10 in titration 4. So it is 10 in power 10 in power 10 in power 10 4 times. Someone may be familiar with skews numbers, is some of mathematical terms in number theory. I think it is one of the primes or numbers which are help us to find the prime numbers. So smallest skews number is 24 titration 4, or 24 in power 24 and power 24 and power 24. I need to say that it is much bigger than any real object in our universe and real anything that you can imagine. And for now, I need your help, because each time I will need to say significantly larger, and I need special words like enormous larger. I don't know. So I will want your help to find new word to bigger. So
universally larger. Maybe.
So we have two arrows, hexalog, heptalog, and so on. For example, Giggle Clank is 10 tetration 500,000. It is tower of powers of 10, is 10 in power of 10, power of 10, power of 10, power of 10, and size this tower is 500,000. So you cannot write this number, or almost cannot write this number with the powers. And we go in to large numbers. And the first large number I want to present, the really important numbers have names. I must to say, first of all, that this is not just a number. The rule that we have numbers which was used in some scientific proof or some scientific paper. So it is not just invented numbers, but someone used this number. So the first big number we know is grid 33, or 3 tetration. No, it is pentation of 3. What is the number? Is by the rule, it is 3 times 2 errors, or it is 3 times 1 error and 3 times 1 error. If we do calculation, at the end we have 3 in power of 3 and power of 3 in power of 3, and the size of this tower is 7.5 trillion. It is, now I need the much more bigger than all that we know and seen up to this point. Yes.
We're getting into a point that even the description of the number can't be withheld in a memory of a computer, for example. Like if you want to just print.
If you just want to write 7.5 trillion numbers of 3, it is you cannot. But if you want to say it is 1 and then write zeros, you cannot not hold them in the computer. You need more. You cannot hold this number in the universe, because to hold the number, you need at least one particle to do something, to move electron or something. But this number is much more bigger than any particles in the universe. So it is not enough universe to hold this number, to write this number with regular notation. But we have much bigger number. For example, tetron, or decataxis, or Grigol. So what is decataxis? It is 10 in power of 10 in power of 10 of power of 10, and size this power like this number. And what is this number? Is 10 in power of 10 power to the power of 10. And what is the size of the tower? Is like this number. So this is enormous tower of powers that it's hard to imagine. We quickly arrived to the situation that we may just write the notation and say it is very big. It is enormously big. It is so huge. It is infinitely big. This number is infinitely big than this number, or something like this. But you cannot imagine. But you try. So are we finished? No. We need a new notation, new scientific notation, because very quickly we will finish the Knut notation, and we will need something more powerful. Yes, Michael.
You said that all these numbers were used in some research or articles or something.
3-3 was used, yes.
Only 3-3?
I don't know. Yes, I know about 3-3.
I think so. It's the gram number. I think the 3-3 is the largest.
Yeah, 3-3 is a part of the gram number.
Yeah.
So
This is so I will touch a little this.
the question is where all of this used, since okay, we can
First of all, this is the conversation that you have in the Googleology itself. When someone drops the number, there are some people that says that it is interesting by itself to name this number and investigate. So we have old school that says the first Googleologists or first people who used these big numbers were not Googleologists. They just write a scientific paper, and they just in one of the proofs they found those numbers. But the new wave or new school says to investigate these numbers and their abilities or their interactions. It is interesting in itself. So 3-3 is the old school. It was used in real proof, and this is the continuation of Googleology. So we need a new scientific notation, and it is fast-growing hierarchy. It is a function, and the rule is as follows. The 0 f0 is the linear function. So 0 of n may be n, or any linear number. And then index a plus 1 says that this is the function n taken n part. It is f a of n. It is says that f a taken f a n times. So a relation to Knuth's notation of hyperoperators, it is the hyperoperators. So f1 of 3 is 3 multiplied by 3. f2 of 3 is 3. It is f1 of 3 taken 3 times. It is 3 arrow of 3. f3, it is titration, 4 pentation, and so on. What is the limit ordinal? Sometimes this number is so huge, or this power of number so huge, that we reach some limit. From some point, function of 10 equal to function of 11. Or if you look on the power of towers, it is so big that if you take several other numbers to add to this tower, or you just cut this tower to several numbers, it does not matter. It is the same the same scale. Or you can say that you can just take 3 and then 3, 3, and then 3, 3, and you have some sequence. And when you go to a really large number, you can say that you reach limit of this sequence, and it is, we called it that we reached the infinity, but in number theory, we say that we reached a first transfinite ordinal, or small omega. And this function is called small omega. This is infinitely large number. So we have really a large number. The numbers which Knut notations were almost unable to represent. For example, gigatree. It is 10, and number of errors of hyperoperator as 10, 2 errors, 100. Just to remind you, then we said 3 errors of 3. It was an enormously large number. It is 3 in power of 7, with size of the tower power 7 trillion. And this is the number of errors, this large number. Yes, Niv.
I don't understand the W notation, since I guess f omega f3 100 is a finite number. It's not infinity, right? So what is omega? It shouldn't be infinity, right? It's not the infinite ordinal. If
I'm not really good in this explanation, but you say from some point of view, we said that no matter which number you have, so you from some number you go to the function and you have fn something, and then you can see on the sequence of function and say that from some point you reach a limit. So no matter that f of k equal to f of k plus 1 equal of k plus 2. So you do something from analysis. You find the limit of the sequence of the function, and no matter which is n. So
but I realize this is probably kind of an order of magnitude, because we are talking about natural numbers.
Yeah.
So limits will not work here, but order of magnitude for limits. And I understand that you have different of order of magnitude between different type of functions here. But it's hard for me to understand the limit process. But let's continue. I think
this is some notation that mentioned it is no matter if you have for 11 or 12 or 30 or 100 or a million here. This function goes to infinity.
To infinity? Okay, never mind. Let's leave this.
Yes.
Sorry.
Yes.
Can I just a quick question? This omega would be less than Aleph 0, right?
No, I will touch.
Oh, no? Okay.
This is the excellent question, because I have the next slide which explains this. So we have the first or second big number, which is called Graham's Graal, or G1. If you remember, the first big number is grid 33. So G1 is 3 4 arrows 3, or 3 where the number of arrows is 3 number. It is the really huge number, enormously huge number. Oh, place your word here, and this is his notation, and this is not enough, because we are going to really big number which called Graham number, and it is very famous because in 1980s it was in Guinness record books as largest number ever used in my math scientific paper. So what is the Graham's number? We have something called Ramsey theory, and Ramsey theory looks like interview questions. So the formulation of all these problems is very easy. You have some geographical object, you color it, you remove some edges, you add some edges, and you need to find something, count something. And here is the Graham's problem. You have hypercube of 2 in power n vertices. You color each edge in some coloring red or blue, and you must find, no matter how you color this cube, it is always will have this graph, single colored complete subgraph on 4 coplanar vertices. So the question, what is the smallest n that no matter how you color this hypercube, you always find this graph? Something I see that something I miss. No, maybe I don't miss nothing. But this is the problem, and it looks very easy. And this is the Grams number. So G0, Grams 0, it is 4. G1, we said it is 3, where number of arrows is grid 3. And then your next Grams number, G2, is 3, where number of arrows like this number. I can say that G2 infinitely larger than G1, G3 infinitely larger than G2, and so on. So Grams number is G64. And we already reached the end of the Knut notation, because Knut notation, you cannot write this number with Knut notation. In terms of high growing hierarchy, we reached after infinity. We reached to infinity plus 1. And do we finished? We reached to infinity. No. And I want to explain what Renan asked. So if we look on the number has two major roles. It is volume of the object. So you have 5 apples. It is called cardinal number or cardinality, and the order from start, it is 5th apple from start, it is order, it is ordinal. So number has ordinal number and cardinal number. And numbers that we are familiar with, we don't say it is ordinal or cardinal, because each number plays 2 roles. It is also ordinal and cardinal. 5 apples or 5 fifths in the row, it is the same 5. But when we reach to infinity, we have 2 different sequences of numbers. We have cardinal numbers. How many numbers you have in infinity of natural numbers? Aleph 0. But Cantor, the same Cantor which created Aleph, Ephes, and cardinal numbers, he wrote about ordinal numbers, and he used the some axioms of the number theory that says that for each number that we have next number, and now we know this axiom as theorem of Zorn that says that any monotonic sequence of number has supremum. So numbers from 0 to infinity, it is monotonically increased sequence, and by Zorn lemma, it must have supremum. And Cantor says that this supremum is omega. This is small. This is the first transfinite ordinal, or omega. And then, because omega is the number, we have omega plus 1, omega plus 2, omega plus 3, omega plus 4, and we can reach 2 omega and omega square, and we can take Aleph 0 iterations of omega and receive omega in power of omega. Once again, the volume of all this still Aleph 0. So from point of volume, it is infinite number, countable infinity. This is Aleph 0, this is Aleph 0, combination of Aleph zeros, you know, it is Aleph 0, but from the ordinal point of view, we can count where our place. So we were here, and now Grams number reached to omega plus 1. So we here in the numbers. And to continue, we need to present a new notation, more powerful. And this is the Conway notation, the same John Conway, which invented life automata. So he represents error, also a chain of errors. And I will not stop on the rules, but what important, A arrow B is A of power B. A arrow B arrow C is A, B, and the number of Knut arrows in power of C. So it is C times arrows of B. For example, 2, 3, 2, it is 2, 3, and 3 with the operation of 2 arrows, it is 16. 2, 4, 3, it is 2 and 4, and the operation of tetration, and this is number 2 in power of 2 and power of 2, 65,000 times. So it is already enormously big number. So Google is very simple. It is 10 in power of 10. Googleplex is 10 in power of 10 in power of 100. Giggle is this number. Great 33 is this chain. Graham's Graal G1 is 334, and Graham's number is this number. So we can continue to work with the numbers which are bigger than omega. But if we are already in omega level, we can find omega plus 2, omega plus 100, omega plus omega. And I want to remind you that, that this function is operator. So no matter, you can say n equal to 10. So this function says 10 and then infinitely plus 2 amount of arrows of powers, and it is tower of powers n in power of 10 in power of 10, and length of this power is the sequence of numbers which are infinite. So we can continue to omega, 50 omega, omega in omega square, and then we reach to interesting number Thrangle. It is the end of Conway notation. So this omega square you can represent by Conway, but omega in power of 3, Conway notation already cannot write. So we have tetratrigonal, which is this function in fast-growing hierarchy, because not Conway and not Knut notation can write it down, but we can continue. And how we continue? We can go to omega in power of omega, and then omega in power of omega and power of omega. And when we continue, and in some point of time, we have infinite indexes of omega, and we stop. Because when you take this power and increase in power of something, you still have this same power, and this is called epsilon zero, or small Cantor ordinal. And this small Cantor ordinal was used in the mathematical proofs in one of 23 famous problems of millennium. It was, I think, it was used in proof of continuum hypothesis. So the small Cantor ordinal is the number. It is infinitely big, but it is still was used. So are we finished? No, because of word small Cantor of ordinal. So we reach epsilon level, and how we can continue? Because we cannot add here nothing. So we use the same theorem, that we have sequence of numbers. We know what is 0, we know what is 1, we know what is omega, and we know what is the sequence of omegas till infinity. And this sequence have supremum. and this supremum is epsilon 1. So by epsilon 1, we can build another number. The axioma that if you have number, you can add to it 1. So it is other number. And then omega in power of this number, omega in power of this number. So this is a completely new sequence. And when you reach infinity, you can go to epsilon 0, epsilon 1, epsilon 2, and so on. But sometime you continue, and you can continue to epsilon omega, even to epsilon 0, epsilon 2 zeros. And I remind you that what this means. Here you need number, but in this such small numbers, you no matter it is 3 or 4, what it says, it is 3 in power of 3, in power of 3, in power of 3, and length of this power as this function. So I cannot even say that it is infinitely large number, because it is infinity in power of infinity large number. But sometimes we can go to the function is epsilon, and we go to infinite indexes of epsilon. So we reach to another limit. And if it is end, no, we go to big Cantor's ordinal or zeta 0. And now we have function of zeta level. So we have zeta 0 plus 1, zeta 0 plus 2, zeta epsilon in zeta till we reach infinity, and we have zeta 1, zeta 2, and more and more and more. We can continue. And it is not interesting to name.
Vlad, can I ask?
Yes.
I'm a little bit. I'm a little bit. This understatement. I'm totally lost where we are right now in the scale, like Cantor scale, where like is Aleph 0, Aleph 1, Aleph, you know.
So
we're
we're still in Aleph 0,
We're
because
still in Aleph 0. Okay.
from the point of cardinality, you still encounter in natural numbers. Each one of these number, it is number. So you in the natural numbers, and you below Aleph 0. But it is not interesting.
No, Vladi, that is not totally. It's not a finite number. The cardinality of all these infinities is Aleph naught, but they are already Aleph naught in cardinality. They are not. They are ordinals, but they are not numbers. They are not finite numbers for sure.
But it is still number.
But we're still countable also, right? So everything is still countable. So we're not really like, it's kind of
Yeah, it's
still,
countable. Yeah, they are
everything is
countable.
still countable, right?
But
So
still
we're still kind of
uncountable
more than
number.
infinite. So not-
Yes.
So it is not interesting to continue. So we go to new hierarchy called Veblen, Austrian mathematic, nearly Oscar Veblen or Oswald Veblen. And he said, you count something till you reach some limit, infinite limit, and this is the fixed point. And then you break up fixed point and break up fixed point. So I will build hierarchy. Function of first fixed point is omega, second fixed point is epsilon, third fixed point is zeta. And you can continue Fiat 4, Phi 5, Phi 6, and you can continue till you pass infinite number of fixed points, omega. And then you can continue and go to epsilon number of fixed points and zeta fixed points. And you can see phi from phi, from phi, from phi, phi. And when you go to infinite number of powers of this function, you can go to function of 3 parameters, and it is the Veblen ordinal or gamma 0 and gamma big, to point that this is the real big number. But we still continue and go to 4 elements, 5 elements, and so on. And in the limit of all this function called small Veblen ordinal, SVO. Small Veblen ordinal is the maximal number that you can write with the Veblen function. And now, at the end, we reach the really big number. And first big number is 3. Also, very, very simple. You have a graph of x nodes, and the next graph, which is no more than x plus 1 nodes, no more x plus 2 nodes, and you have rule that previous graphs are not part of the next graph. It is not so simple as I say, but I have no time. I have only 6 minutes to finish. So this is the 3 problem, and 3 of 1 is 1. 3 of 2 is this, and the red one. And 3 of 3 is anomaly large number, infinitely larger number than Graham's number. Or if you remember small Veblen ordinal, it is infinitely 3 of 3 is bigger than infinitely big tower of powers of Graham's number. And it is lower bound. This is, I am not understand this notation already, but this is its bound. So are we finished? No, we have insane bigger number than 3. This is the number of subcubic graphs. Also, you have Ramsey theory, very simple. You have graph of n vertices, graph minor that you exclude one or a couple of nodes from the graph and erase all the edges. And you have sequence of graphs G, each one of the at most I plus k vertices. So you G1, G2, G3, and each next G not contain previous graphs as its own minors. And you must to find maximal lengths of these subcubic graphs of lengths key of vertices key, and we know that subcubic graphs of 0 is 6, and you just can write it or draw it. But as this number are larger than all that we see up to now. It is enormously larger than 3, and it is greater than halting time of any Turing machine if it halts. And this is much psychopathic larger than 3. But we have infinitely biggest number than SCG, and this number called BB, Busy Beaver. And this is the part of investigation, what is the limits of Turing machine. So why it is Busy Beaver? For non-mathematician, you have explanation that you have hotel. In the hotel you have rooms, and you have lights. And you have Busy Beaver, which have a couple of states. For now, you see 2 states. He may be a scared state, or he may be not scared state. So this is the Busy Beaver of 2 states, and we can think about Busy Beaver of n states. And we have proof that Busy Beaver of n, that function Busy Beaver, uncomputable on Turing machine. It says that it grows faster than any computable function, and we cannot compute. We can only check all the possibilities, or try to mathematically prove something. So the question: you have Busy Beaver of x states. what is the longest sequence of ones you can receive till the Busy Beaver stops. And it is Busy Beaver of 1 is 1, Busy Beaver of 2 is 2, Busy Beaver of 3. So it grows not fast. But then you see that 6 is enormously big number, and you see the difference because it is from one paper and this is from another paper. So this paper just took hyperoperations of 3, and we can prove then that Busy Beaver of 18 bigger than Gram number. And Busy Beaver, one of the papers says that Busy Beaver of this number bigger than SCG, bigger than 3, and this number is out of our mathematics. ZFC says Zermelo-Frenkel axioms with the choose, and the latest result that in July 2023 was proof that Busy Beaver of 745 can be proved under Zermelo-Frenkel with choose axiomatics. So it is out of our mathematics. And does it the biggest number? No, we have the really last number. It's called Ryo number, and it is already out of fast-growing hierarchy. We cannot write it down mathematically. We can write it by symbols of first-order logic. And what it says, you see, I use some alphabet and some rules to describe the numbers. So this is the enormously big number, but I can describe it by rather small number of symbols. So this number says, if you have some alphabet and you can explain it with this alphabet large number, and you have Google symbols to describe this number by describe large number by Google symbols. This is the larger number that you can write using Google symbols in any mathematical any system of first order logic, and this is the bigger than all that you want to imagine or say. So we finished the last slide. Still, how big this round number? It is still in Aleph 0, and we can talk about numbers here, and maybe this, and still there are someone that says the biggest number is 42. Thank you very much, and we must drop and go to another meeting. Thank you.
Thanks, Radi.
Amazing.
Thank you very much.